The May 18, 1980 eruption of Mount St. Helens was a seminal moment for volcanology. On that fateful morning, an earthquake and giant landslide uncorked a lateral blast that flattened 230 square miles in a matter of minutes. For 9 hours after that, a vigorous eruption column billowed into the atmosphere, coating everything downwind with ash. Local rivers were inundated by mud flows and debris flows that took out bridges and homes for miles downstream. For 2 months prior to May 18, 1980, scientists for the U.S. Geological Survey and the University of Washington's Pacific Northwest Seismographic Network were closely monitoring Mount St. Helens.
But it was truly only the beginning of an eruptive episode that lasted for a little over 6 years. So the first explosion occurred on May 18, and then there were several sizable explosions in the summer of 1980. And they sort of trailed off until October of 1980. And then for the next 5 years, or 5.5 years, there were a series of dome-building eruptions in which molten material came out, very viscous, pasty lava came out on the floor of the crater and piled up to form a dome or a mound in the middle of the crater floor, a feature that's now about 900 feet high, sitting on the floor of the crater. So this episode at Mount St. Helens, which began on May 18, actually culminated in October of 1986 when the last magma came out of the ground.
The volcano reawakened again in 2004, displaying another period of dome building and smaller explosive eruptions. This resumed unrest was an opportunity for the scientists to deploy new and improved monitoring equipment.
Today we deployed with a helicopter and a multi-sensor instrument package that was developed literally in the past week, or at least fabricated in the past week at the Cascades Volcano Observatory. This was in response to what we've been learning about the volcano over the past 2.5 to 3 weeks. The first thing we did was deploy ground deformation instruments out on the outer flanks of the volcano and learn that they weren't moving. Then last week we deployed 3 GPS instruments on the old part of the lava dome itself, and discovered that it's moving very little, if at all, at the same time that the feature on the south crater floor is moving by tens of meters. And so we wanted to get instruments directly on the part of the dome that's moving so dramatically. And so we very quickly put together a GPS sensor, a seismometer, a tilt meter, and a microphone. The microphone will record the sounds of explosions should they occur. And that's important. If they occur in the middle of the night or in bad weather, we'll have some indication that that's what's happened and integrate that into the rest of our data stream. We'd like to know, for example, is the deformation continuing? Is the rate increasing or decreasing? How does the rate correlate with seismic activity? When we're having more earthquakes, is the ground deforming more rapidly or less rapidly because it's easier for magma to move up the pipe and therefore producing fewer earthquakes? We don't know such fundamental things, and understanding those kinds of relationship is key to our trying to interpret the processes that are going on, understand where the volcano might be headed, and therefore mitigating any hazards associated with future activity.
Volcano science and volcano monitoring have developed impressively since May 18, 1980. Technology such as GPS, infrared imaging, acoustic flow sensors, and Doppler radar are just a few of the new tools available to the scientists. They are studying hazards from lava flows to explosive eruptions, mud flows, debris avalanches, and airborne volcanic ash. The realization that volcanic ash can stall a jet engine adds urgency to monitoring explosive eruptions and any ash clouds that may threaten aircraft. In the U.S. and its territories, there are 169 volcanoes capable of erupting. With responsibility for monitoring these volcanoes, the USGS now operates volcano observatories focused on Hawaii, Alaska, the Cascades, Yellowstone, and Long Valley in California. One important aspect of this operation is the Volcano Disaster Assistance Program, VDAP, a team of scientists with a cache of monitoring gear that responds to volcanic unrest across the planet. Among the VDAP success stories was the forecasting of the 1991 Mount Pinatubo, Philippines eruption in time to save thousands of lives and to evacuate planes and people from U.S.-run Clark Air Base. Awe-inspiring, spectacular, and scary all characterized the eruption of Mount St. Helens on May 18, 1980. The human response to this catastrophic event has laid the groundwork for saving lives and better addressing future volcanic eruptions wherever they might occur.